Hello everyone, hello YouTube. It's October 4th, 2018, and this is Brian, and this is my second video. If you've seen my first video, you will notice some things that maybe you're not familiar with. One of them being what we have on the screen here, a contour integral. If you've taken calculus before, you may know what a regular integral is. But you might not know what a contour integral is, and they're actually kind of really similar, and that's what we'll talk about in this video. My goal for this series is to teach people complex analysis and number theory and just the personality of the numbers in general, and I just really want people to go down the same rabbit hole that I went down the last couple years. It's quite exhilarating and fulfilling, and I recommend it for anyone. So let's do it. The title of this presentation is what is a contour integral, and what you need to know is before you go on this rabbit hole with me is you need to know calculus. They teach it in high school, they teach it in college. You need to know what a derivative is and an integral, and hopefully you've gotten to infinite series, because when you combine all three of those things, a lot of magic happens, especially when we go on to the second thing you need to know is you need to know that imaginary numbers exist. The square root of -1. Accepting the fact that square root of -1 is a number, and it is a solution to a polynomial such as x squared plus 1 is equal to 0. A lot of magic happens, and you will soon see. It's incredible when you combine these two things right here, how much magic happens. Combining these two things, you can get stuff like this, 1 plus 2 plus 3 plus 4 ... Make these dots a little bigger. Basically, it goes on forever for all infinity, and you would think that it's that this sum would equal infinity, but it doesn't. It actually equals to -1/12, and that's what my first video talks about. But I feel that no one knows what the hell I'm talking about in the first video, so that's my goal of this series of videos that I will be making now, is getting people up to speed and introducing people to the concepts of complex analysis, and then into topics that are very on shaky ground as fractional complex analysis. So let's just continue on here. So those are the two things you need to know. So just a reminder, a regular integral from calculus, you got a curve here, a function f of x, and it just, kind of just does its thing on the xy plane. And an integral, all it is you pick 2 points A and B, and you figure out what the area is under the curve with respect to, the x-axis. As you can see over here, there's a positive area, there's a negative area, and there's a positive. So this negative area will cancel out some of the positive area, and you'll get some sort of number like, how much total area is beneath the curve f of x from the in the interval a to b. You know what I'm saying? So that's one of the prereqs that the viewer needs to know to continue on. But so what is a contour integral? Let's just look at the domain here. Let's just take that same integral. The same integral from the last page here, and let's just look at the domain. Let's not even worry about what the actual function looks like. Let's just look at the path that the integral takes. We start from A, right over here. Oops. Right here. And then we go to B. Okay, that's basically the path you take in this integral, and then you integrate on that path. So the question is if you start at A and you go to B, you'll get some number, in the next slide here, we will see that what happens when you return to your home location where you started. So let's add another integral. So the function is still the same. This is still the same function, f of x is still the same. Whatever, it's just a generic function. You know, it could be the sine function, it could be the exponential function, it could be anything. It's just imagine some simple elementary function, and this blue one, you're going from, you start from A and you go to B. Start from A, go to B. On the second one, we're flipping the interval here. We start from B and we go to A. So we start here, and then we basically make a loop. Okay? We basically make a loop. If we add these two together, what happens? You get 0 most of the time. Most of the time you get 0. And why is this? Because when you flip the interval like this, it really is just the negative of that integral. And if you remember from calculus, you'll see why that is true. And also, it's just intuitive. If you start at A, go to B, and then you go from B back to A, you're back where you started. So the sum of these two integrals should be 0. This is a contour. We just did a complete circuit, and that's all a contour is. Now, if you look at this, I'm going to try really hard to do this, but look at this. There's our little path there. Sorry if you can't see that, but you start at A, you go to B, then you're at B, and you go back to A. You made a counterclockwise path where you return to where you started. And we're going to call this contour, this path that we took, C. And that's all this is. That's all. See this integral down here? This is the contour integral. Right down here is a contour integral, and this equals, if you really want to get explicit and calculate that integral, you would break it up into two explicit integrals, and then you just calculate them. See, look, this interval, and that is how you calculate. And most of the time, it will equal 0. Okay, and it's just that's really it's intuitive why that should be. Take some time to think about it. If you take, let's just go back to this first one here. You know, if you start at A and you end at B, you'll have some area. But if you go start at B and then go back to A in the opposite direction, then it's just the negative. It's like the way I think of it is you're on a hilly terrain at a park. You know, you start at a point A and you walk around to maybe a distant tree, and we'll call that point B. Yeah, you're going to go up some hills. You're going to go down some hills. Your total change of elevation change will be some number at point B, but then when you go back home to point A, all that gets reversed. And what we'll find is your change of elevation is not only 0, but it's path independent. So, but even if you go a different path back in that park, you're still, when you wind up at A, you're still gonna have the same change in elevation. So as you can see in this new integral, this new path, as you can see right here, this new path, you're still gonna end up at the same point home, and you're still gonna have the same change in elevation. And that's really how you think about it. So this will also equal 0. Sometimes. We're going to get into that. Most of the time, really. Okay. So let's prove that. What I'm going to do here is I'm going to take a generic polynomial of one term, you know, x squared, x cubed, x to the 4th power, x to the 5th power. I'm going to go ahead and just make it generic and just call it x to the n power, where n can be just any integer at this point. Okay, and what we're also going to do is we're going to go around, as you can see in this origin. Keep in mind that because we're accepting that complex numbers exist, that now instead of being confined onto the real line as in regular calculus, we can take different paths. So we can go in a nice circle here, a nice little circle, see, because now we have more room to breathe. So what is a good way to make a nice circular path without any headaches? Well, that's just, of course, using the substitution x is equal to e to the I theta. As you can see here, we're going to go ahead and make that substitution. For every x, you just put in the e to the I theta. Of course, you'll get a term here and then a term here that you'll have to take care of by differentiating. And on the next term here. And I highly recommend anyone pausing the video and just kind of working this stuff out on paper. Math is all about the struggle with a pencil and piece of paper. And I truly believe that you do not learn mathematics without putting on, getting that painful struggle out on the paper. You need to go through that to learn. I have never learned anything by just watching a video. You learn big concepts, and that's what this video, my goal of this video is. But if you really want to understand, you need to just do these lines. Hopefully I've picked out the right lines to get you the basic concepts down, because we're going to get into some big concepts here. And if you don't know how the math works on the back end, then you just won't understand it. And I promise you there's some big stuff coming. So on this third line here, we made those substitutions. We have this one, of course, is from the differential with the I, that the I got popped out. This one is from the x to the n term, because you can see this little n here. Combining these exponentials, you'll just get e to the I theta parentheses n plus 1, and then times a constant I d theta. And of course, since we're going around a circle starting at angle 0, and we're going around 2 pi radians, our integral is from 0 to 2 pi. So let's go to the next slide here. And once we solve this integral and find the antiderivative for that function, we come at this, and we are at the end here. And then, of course, substituting in for theta and doing finding the antiderivative over here, you're left with this term right here. And it seems that for every n in the integers, except one very specific example, which we'll get to later, these will just cancel out and equal to 0. So the next question is, oh, Brian, you did a circle. Why can't we just do a square around the origin? So that's what we're going to do here. As you can see, I have, instead of a circle, a blue circle, I have an orange square that I've meticulously drew on a PowerPoint for ya. And, we're starting at here. We're going, oops, sorry, I'm really bad at drawing. In a counterclockwise direction. Direction is important. We'll get to that later. But we're going to do the same function, okay? The same x to the n function, where n is any integer. As you can see that this can be broken up, this contour integral can be broken up to 4 different straight normal integrals. And this is what you see here is this shorthand. So I don't have to, write all this nonsense in here for everyone. So hopefully you guys get this, that this over here is equal to this big mess. And then these are just regular integrals. And they imagine each one of them has, an x to the n dx for every one of these. Okay. And then our next slide, we can just simply take the antiderivative of x to the n, which is, of course, x to the n plus 1 divided by n plus 1. and then just put the endpoints of the interval on each bracket. And it's really, you can see quite easily that, when you do the math, let's just do this first one. What is this? I n plus 1 over n plus 1 subtracts, because remember you have to subtract. Now you have to subtract this part. 1. So I'm going to make this I a little bit better. I'm sorry, I'm really bad at this. And this is a 1. This is just to remind you how to, solve it like normal integrals from calculus. 1 to the n plus 1 power over n plus 1. Really horrible drawing. But that's what each of these brackets mean. And you will see that this one will, if you do the math, I highly recommend just doing it on paper and seeing for yourself that this one will cancel out this one. This negative 1 will cancel out this negative 1. Because it'll be added. Just do it on paper, and I promise you that they will cancel. This one will cancel on this one, and this one will cancel on this one. So this will equal 0, and we'll see that in the next slide. Yes, it equals 0, and yes, 0. So now we're going to get to one of the big results. One of the big results. Koshi's integral theorem. This is just kind of like a baby version. There's a more mathematical generalized version, but since we're working with these simple polynomials to begin with, you might as well just keep it in that format. What this theorem says is that if you have these simple polynomials and you have a path, let C be a contour that walks around the origin in a counterclockwise direction. So, we have an origin here, and, we have a pathway that, it does whatever it wants. Doesn't cross the origin, but it goes in a counterclockwise direction. This will always be 0. This makes sense. Just imagine a park. The polynomial that's within the integral represents the terrain, the change in terrain. No matter how you walk around that park, and if you end up at the same location, your change in elevation will be 0. And that's what I said down here. N could be anything, any whole number except 1. And we're going to get to 1 right now. So what about n is equal to -1? Because if you remember, this is kind of like the main ending calculation for the contour. If n is equal to -1, what happens? Well, you got this weird thing. I'm going to draw it right here. You got a weird kind of paradox that, you have 1 over, oopsies. That should be a 1. Sorry, guys. Sorry, I'm really bad at this. You got 1 over 0 minus 1 over 0. And that just creates some crazy nonsense. So what happens? Let's just do it. The best thing to do is just do it. So we start out with this integral, which is we're just doing f of x is just 1 over x. Weird things happen at 1 over x. Keep in mind that everything is normal when we integrated a function like 1 over x squared or 1 over x cubed. Go back and realize that it's for any n besides n is equal to -1. This is the only function that if you walk around, something different happens. And let's just see what happens. So yes, we have this again. It gets broken up into 4 different paths. And if you know the antiderivative of 1 over x, you know that it is the logarithm. And the logarithm is crazy in complex analysis because values like log -1 has values. Maybe we'll get to that in another video. But for example, log of I is equal to pi I over 2. Log of 1 is, of course, 0. Log of negative 1 is pi I. Log of I is, of course, negative pi I over 2. The same as over here. And it keeps going on. And you're left with the result of 2 pi I, which is not 0, which is very surprising. And you may be thinking, well, wait, that's crazy, Brian. That's crazy. Well, let's just see what happens. The substitution for e to the I theta. Let's just do that calculation. So you have the same contour integral where you walk around the origin. Where in the origin, that's where the singularity is for 1 over x. So you can't go to the origin, but you can walk around it. That's the big concept that you guys all need to get in your heads. So we're going to do the substitution e to the I theta. Of course, we have to deal with this new. We have to take the derivative of that, and it's also we have this down here now, and as you'll see that when we do that, when we took the derivative, an I pops out just like before, but look at this. We have an e to the I theta up top, and we have an e to the I theta on the bottom, and they just cancel out and turn into 1, which as you can see right here. So we're just left with the integral of the imaginary constant I times d theta, and we still have the same interval of angles that we have to go through from 0 to 2 pi, and so we're left with 2 pi I. You can also do it explicitly by taking the antiderivative first, where you're left with the complex logarithm, and then substituting in for x equals to e to the I theta, and you're also left with 2 pi I. And like I said, pause the video, do it on paper. I highly recommend it because in the next couple videos, it's going to get pretty insane. It's really going to get insane. And I really it'll be very entertaining when you see what's going on here. So we're going to kind of summarize what we learned about this in this video. Basically, let C be a contour that walks around the origin in a counterclockwise direction. Just simple polynomials with one term of order n, where n is an integer. You will either get 0 or you will get 2 pi I in the case of n is equal to negative 1. And that's it. That is basically all that this video teaches. That if you are in a park, most of the time you walk around the park on any path that you choose and you end up to where you started, your change in elevation will be 0. But if you walk around a singularity of order 1, or this simple 1 over x, if there was a singularity of that order in the middle of the park and you walk around it, your elevation may be the same, but your phase changes by 2 pi I. And that's pretty metaphysical, I think. I don't really understand what that means, but it's probably one of the most powerful statements in math, because in the next video, we'll see why that is so powerful. And we can really, it's what I would explain or describe as fishing out residues and really just kind of fiddling with the numbers. Really, that's what we're going to do in the next videos. We're going to start fiddling with numbers and get some real powerful relations. So, that's it. I'm gonna, send me some pizza money. I'm hungry. I really want money. Look how cute you are. Look how cute. Ah.